In this video, we're going to start talking about something called covalent bonds. And up until this point, we've been talking about atoms either giving electrons away or taking electrons from another atom in order to get to that stable 8. But there are just some atoms out there that it doesn't really make a ton of sense to give or to take. But instead, they're going to do something a little bit different. Instead, they're going to share their electrons with multiple atoms. So here we go. So basically, here's our learning target. We're going to again focus on valence electrons because those are the ones that are most influential when we're talking about bonding. Things that we're going to need to remember how to do for sure. Make sure you know how to do Lewis dot diagrams. From the Lewis dots, we need to understand the number of valence electrons atoms have, and then use that valence number to predict how atoms are going to react. In this case, we're not going to have any ions, neither positive nor negative, because atoms are not giving or taking. In this case, we're really going to focus on how one atom shares with another, or how one atom shares with multiple atoms. So we're going to focus on which elements. There's specific groups of elements on the periodic table that will form covalent bonds. What happens to the electrons when a covalent bond forms. Again, we're going to be doing some drawing of these bonds. In this case, we're going to have multiple types of covalent bonds, single, double, and triple, and I'll show you how to do or to draw each of those. And then what are some properties of covalent compounds? We'll probably get to that in the next video when we're dealing with polar and nonpolar molecules. Okay, so here we go. Why in the world do we need to have covalent bonds to begin with? Well, like I said in the beginning, some atoms, it doesn't make a whole lot of sense to gain or to lose electrons. And this is where we kind of get into the sticky area of elements in groups 4 and 5, these guys right here. Remember, atoms are extremely lazy when it comes to becoming stable. Everybody wants to become stable, but they want to do it in the easiest way possible. And if you notice, what we're dealing with are mainly nonmetals, right? If we're over on this upper right hand corner of the periodic table, and most of these nonmetals, it's just very unlikely for them to gain or to lose electrons. And we kind of started this conversation with carbon right here. Okay, so we got carbon. It has four valence electrons. What's going to be easier to give 4 electrons or to take 4 electrons? Well, in the grand scheme of things, it takes the same amount of energy to give 4 or to take 4, and it takes a massive amount of energy to do that. So instead, carbon doesn't do either one. Instead, it finds other nonmetals to bond covalently with to get to its stable 8. There are also quite a few elements in group 5 that will do this as well. Again, it takes a lot of energy to gain 3 electrons or to lose 5 electrons. So in some instances, they'll bond ionically, but in most cases, they're going to bond covalently. So just to recap, when you transfer electrons, it takes energy to do that. When you're only transferring 1 or 2, like lithium or magnesium, the amount of energy to do that isn't very, very much. However, over here in group 4, you're moving many, many more electrons, which takes way too much energy. And just remember that these guys are extremely lazy. So it's a lot easier to share to get to your stable 8 than it is, in this case, to give or take. So, when atoms share electrons, they form a covalent bond. Okay, so the definition is the attraction. Okay, so this is what's holding these atoms together. This kind of mutual attraction towards one another in order to get to that stable 8. So the attraction that forms between atoms when they share electrons is our covalent bond. Just like in ionic molecules and compounds, we end up with something that's neutral. Okay, remember in ionic, you had like a +1 ion bond with a -1 ion. They cancel each other out, and the whole thing has a neutral charge. In this case, it's even easier to understand because we're not even giving or taking electrons. Okay, we're just sharing them to get to that stable 8. So again, we're ending up with a neutral particle. In this case, that neutral particle is called a molecule. I think the biggest thing to remember here is that covalent molecules, for the majority of what we're talking about, comes from 2 or more nonmetals sharing electrons. So in this case, we're never dealing with metals, okay, because remember, metals, it's extremely easy for them to lose electrons, okay, whereas nonmetals is extremely easy to gain electrons. But in this case, we have 2 nonmetals sharing their electrons. So, what I'd like to do is start thinking about an example of hydrogen. Okay, so we've got hydrogen. If you remember, hydrogen is in group 1 on the periodic table. And it's also a nonmetal. Okay, so we've got a couple of things going for us right now. We've got hydrogen atoms, which is nonmetal. Okay, so if we bond a nonmetal to a nonmetal, we automatically get something that's covalent. Okay. Now hydrogen only has, since it's in period 1, one energy level. Okay. So if it's all by itself, just hydrogen sitting there, right? Here's hydrogen. It's got 1 valence electron sitting over here, right? Is it stable by itself? Well, no. It's close, right? Remember, if you're in period 1, the maximum energy levels you have is just 1, and the maximum valence electrons it can hold is 2. So we're close, but we're not quite there yet, right? So what we can do is we can potentially take another hydrogen and bond it somehow to that other hydrogen. Okay, and that's kind of what we're gonna show you here. So again, just to recap, hydrogen, very, very tiny atom, only has 1 energy level, and that 1 energy level can hold a maximum of 2 valence electrons, or 2 electrons just in general. So if we take 2 hydrogens and we put them together somehow covalently, each atom should end up being stable or happy because its energy level is full. Now, the drawing of covalent bonding is a little bit more complex than drawing ionic bonds. In this case, we need to make sure that we show the electrons that are being shared, but also at the same time we also need to make sure that every single atom in this molecule is sharing enough so that everybody is stable. So, step by step, how do we do this? Well, step number 1 is to just write down the symbols for each element. Okay, so here's step number 1. Over here in the drawing, we did that. Okay, so we have a hydrogen right here, and then we have a second hydrogen right here. So that's taken care of, step number 1. Now we need to draw the Lewis dot for each element. Okay, so hydrogen is in group 1, so we only need to draw 1 dot for each of the different hydrogens. Okay, so far so good. So far, nothing new. Step 3 is where we get to something a little bit different. It says move single electrons between the 2 elements to show that they're being shared. Okay, and what I mean by single electrons is an electron all by itself, like this guy right here. It's not paired up with another electron. Okay, for example, if I had element X and it had 5 valence electrons, I'd put my Lewis dot would look something like this. Okay, so these 2 valence electrons are paired up, and we really can't do anything with these guys that are paired up. All of these other electrons are single electrons, and we can move those in between whatever atoms we want to. Okay, so just kind of keep that in mind. Once we have all of the electrons kind of moved in between, as we have them right here, the two atoms, what we then do in step number 4 is draw circles around each of the atoms sharing the electrons to kind of help us visualize that they're being shared. So to recap, so far what we've done is we've taken one hydrogen, I'm going to color code these things, with 1 valence electron, and a second hydrogen, also with 1 valence electron. All we've done is we've moved the single electrons between them. Alright, so we end up with something looking like this. Okay, and then what we're going to do is we're going to draw some circles. So one circle for the red hydrogen, another circle for the blue. Now what we're going to do is we're going to take the 2 electrons that are shared in the middle, and we're going to turn this overlap section right here into a bond. Now before we do that though, we need to just double check and make sure that every single atom in here has a full energy level, right? So if I take a look at the red hydrogen, the circle that goes around the red hydrogen, I have 1 valence electron, 2 valence electrons. Okay, so that hydrogen is full. If I take a look at the circle just for the blue hydrogen, again I count them, I have 1 valence electron, 2 valence electrons. So everybody's happy the way that they are. So I can continue in my drawing. So I've got my red H, I've got my blue H, and I'm going to turn the dots into a dash, and that dash represents the electrons being shared. Okay, you can kind of think of it as them kind of doing a little bit of a tug-of-war battle between the electrons. Okay, on one end of this bar, or this dash, is the red hydrogen, or the red electron. On the other side of this bar is a blue one. Okay, so they're tied together by sharing those electrons. And then the last step is just to take all the elements and put it into a chemical formula. So we have 2 H's, so I'm just going to write that as H2, which is hydrogen gas. You can't find a hydrogen all by itself. It's not stable. They tend to bond with each other just like that. And hydrogen's not the only element on the periodic table that finds another of itself in bonds. It's actually pretty common. We get these pairs of atoms. We call them diatomic molecules. Diatomic, di meaning 2, and then atomic meaning atoms. So a lot of things in group 7. So group 7 does this a lot. So you've got fluorine, chlorine, bromine, iodine. All those are in group 7. They love to bond with itself, so you get a lot of diatomics that way as well. Now, what we can do is we can bond more than just 2 atoms together covalently. If we think about it, let's take a look at hydrogen and oxygen. Okay, so oxygen's group number, what is that? I think it's group 6. So if it's group 6, it means it has 6 valence electrons. So how many electrons does oxygen need to get to the stable 8? Well, it needs 2. Hydrogen is in group 1. We talked about that, right? And if it's in group 1, it only needs 1 valence electron. So in order to get hydrogen and oxygen to bond together, we're going to need a couple of hydrogens to covalently share their one single electron with the 6 that oxygen already brings to the table. So let's kind of see how that works. Alright, so we're going to draw this out. So we have a hydrogen, right, with its one single electron. We have an oxygen. Oxygen's in group 6. So we're going to have 6 valence electrons for this guy, right? And then we're going to have a second hydrogen with its single electron. Okay. So we need to keep in mind that this hydrogen needs 1 electron, this hydrogen also needs 1, and this oxygen needs 2. Alright, so if we look at the empty spaces, we can see that there's an empty space here that needs to be filled, an empty space here, and an empty space here. Okay, so remember, we can move the lone pairs, or the lone valence electrons, wherever we want. Okay, so what I'm going to do is I'm going to move this electron to be shared in this spot, and I'm going to move this electron to be shared up in that spot. Okay, so I'm going to draw this again. So I've got my oxygen over here, okay, with its blue electrons that it brought with it. I'm going to take my red hydrogen, and I'm going to move that lone electron in that empty spot. And then I'm going to take my black one and just do the same thing on the other side. Now, before we can say that this is the way it's supposed to go, we need to remember to draw all of our circles, right? So I'm going to draw one circle around the red hydrogen and the electrons that it shares. I'm going to draw another circle around the second hydrogen. Okay, if we look inside this red circle, or this orange circle here, there are 2 electrons in there, which is perfect. Hydrogen only has 1 energy level. Same thing with this hydrogen over here. So we are good so far. Now I'm going to draw a circle around all of the electrons that oxygen shares and that brought with it. And if I count those up, I need to get to 8. So I've got 1, 2, 3, 4, 5, 6, 7, 8. Alright, so drawing it this way and having the electrons share the way that they do, everybody's completely stable. So now what I need to do is just put in the dashes, right? So I've got my oxygen, it's sharing electrons with the 2 hydrogens. The tricky part here is that I can't leave it like this. I need to make sure that I also show the unshared pairs, right? Because if I just write it like this, it looks like oxygen only has 4 valence electrons. 1, 2 being shared there, and then 3, 4 being shared there, right? But it also brought with it these shared pairs, or these pairs that it didn't do anything with. Okay, so if I count now, I've got 1, 2 shared with this hydrogen on the left, 3, 4 shared with the hydrogen on the right, and 5, 6, 7, 8. Alright, so everything works out that way, and then that's just plain old water, H2O. Okay, the only thing that's different between the one that I just drew and this picture right here is that this picture is a little bit more realistic because of what these electrons out here do. Those electrons basically push or kick the hydrogens away from it. Okay, and we'll learn why in the next video. But what that does is it causes the actual structure, the shape of oxygen, to be more of this bent shape rather than the linear shape that I showed you, and it's because of these electrons out here. So this is the right way to draw the oxygen molecule. Another thing to kind of keep in mind here is that we can share multiple pairs of electrons between atoms. Okay, it's not like we can only do X is covalently bonded with Y. Sometimes, if it works out and everybody's happy, we could have X covalently bonded with 3 shared pairs in between. Just the only thing you need to keep track of is making sure that everybody stays happy with the number of electrons that they need. A couple of examples of this would be just plain old oxygen. The air that you're breathing in right now has a lot of diatomic molecules of oxygen. Same thing with nitrogen. So what I'd like you to do is just on your own see if you can draw oxygen bonded to another oxygen or nitrogen bonded to another nitrogen. So as you can see, when you bond oxygen to another oxygen, we have these 2 single lonely electrons. And what we can do is we can throw both pairs of those electrons in the middle between the 2 oxygens, and they can share both of them. When we do that, we get something called a double bond, where you have 4 electrons being shared between the 2. And if you want to double check, you can count all of the electrons to get to that 8. Alright, so you got 1, 2, 3, 4 being shared in the middle, but then you also have the 4 electrons that they brought, by themselves. So oxygen has a double bond between them, whereas when we take a look at nitrogen, we get something a little bit different. When we look at nitrogen, nitrogen has these 3 electrons that are all by themselves. We can throw all 3 of them in the middle, and when we do that, they're sharing 6 electrons, so 3 sets, so we call that a triple bond. You can even have a quadruple bond as well. Again, you just got to make sure that every atom gets to its stable number. So, if you need any help with this, go back, take a look at different sections of the video. Make sure you took detailed notes.